Hi there, my name is Christopher Worth and welcome to the third video of Homework 6 for MEB. This video is going over part 3. It's asking us to derive the Rashford-Rice equation for an n-component flash calculation at a given temperature and pressure. Now that's a lot of words, actually it's not a whole lot of words, but it's a little bit complicated. So, per usual, I'm going to start by drawing out a flash situation, a flash reactor. I'm going to swap over to the full screen so you can fully see it. All right. So let me really quickly draw out what a flash reactor is, or a flash container. So we have our container. We have feed coming in, and two flows going out because there are two things in here. There is a vapor layer up here and a liquid layer down here, and I'll mark those. Of course, that means that liquid is going out the bottom and vapor is going out the top. Now, for this, the pressure and temperature must be controlled. It is absolutely imperative. So, in order to control that, usually you would have either a cooling or a heating jacket because the feed might come in at various temperatures. Temperature is, you want to be at 360 degrees Kelvin and, 10,000 pascals. The feed's coming in at 2,000 pascals and 370 Kelvin, who knows. What that means is that we have the cooling jacket. This isn't necessarily important for the calculations, but it helps visualize. And we have this here. Now, the Rashford-Rice equation helps us to figure out what the component from a feed of something, of a mixture, what the mole fraction is of, or the percent of phases is, how much vapor, how much liquid is in, and then how much of the two constituents or two components are in each of those. For example, there might be more, if we're using benzene and toluene from the other parts, there might be more benzene than toluene in the vapor and more toluene than benzene in the liquid, or vice versa, or they might be equivalent. The Rashford-Rice helps us find that. So, to start out, I'm going to rewrite Raoult's law. The marker is starting to fail. And remember that the liquid phase mole fraction multiplied by the saturation vapor pressure is equal to the vapor phase mole fraction multiplied by the total pressure. We remember that. Now, new variable. We know that, or we don't know that, but if xi divided by yi, oops, my algebra is wrong. By doing a little bit of algebra and massaging the equation, we know that the liquid mole fraction divided by the vapor mole fraction is equal to the total pressure divided by the saturation vapor pressure, and new variable, this is equal to Ki. Now, Ki is going to show up in the Rashford-Rice equation. So, let's begin with the Rashford-Rice stuff. The Rashford-Rice equation says that the sum of the liquid phase mole fraction minus the vapor phase mole fraction of all of the components is equal to 0. That makes sense. The mole fractions in the liquid and vapor phase must add up to effectively 1, and then same with vapor. So if you subtract 1 minus 1, it's equal to 0. Now, if you look at this, we have yi here, We have xi here. And we really only want one for use later, because we want to use one, we really only have one equation, we want one variable, or, yes. So we're going to cancel out yi, which means that yi, and we're going to be using ki here, is going to be equal to and if we flip these, it's also true. Yeah, if we flip these, it's also true. That means that ki multiplied by the mole fraction, effectively the pressure divided by the, or the saturation pressure divided by the total pressure. You must flip it if you want to flip these two. They're the reciprocal of both. So that ki is equal to the multiplied by the liquid mole fraction of a component is equal to the vapor mole fraction of a component. Now we're going to put that into this equation here. So the sum that's better, of the liquid mole fraction minus ki liquid mole fraction is equal to 0. Real quick, I messed these two up. It's not overly important, but yeah. And this way, just for equation's sake, because otherwise we would have to do some negative flipping and yada yada. It'll all end up being the same, but just for simplicity's sake, it means that, so if we substitute the ki multiplied by xi minus xi is equal to 0, then we can factor this out. It goes to the sum of xi liquid mole fraction multiplied by ki minus 1 is equal to, 1 there is equal to 0. Now, why does that matter? Well, it doesn't right now. But if we look at this and we take a little bit of common sense and we write a little equation out, we could say that F, if we denote, can you see that? Yeah, you can. If we denote F to be the total moles in the container is equal to V plus L. So that's vapor plus liquid. Now, if we add, remember what we talked about in part 2, the beginning. If we add xi and yi, and then with graphs, I need to draw out a really quick one. In this little part here, we're going to denote this as z1, this little bit here, and this little bit here as y1 and x1. So this, along this line here is y1, the mole fraction of, at this specific pressure, this mole fraction here is, y1, all of the mole fraction is vapor. Over here, all of this mole fraction is liquid. And in here, this is somewhere in the middle. So that's what Z1 is. Z1 is that odd middle state where we don't have all vapor and all liquid. It's kind of a mishmash. So the total mole fraction at this of Z1 is going to be multiplied by F, Z1, equals, now vapor is going to match with Y1. And L, of course, is going to match with, liquid, of course, is going to match with X1. So that means that the mole fraction in, or the mole amount in that weird state is going to be equal to the volume and the mole in the liquid state and the mole in the mole in the liquid state, mole in the vapor state is all moved into that equation. Now, why does that matter? Well, if we say that the liquid is equal to the vapor, the total moles minus the vapor, and then we say that Y1, we substitute this in, we can get a new equation. F multiplied by Z1 is equal to V multiplied by Ki Xi plus L, and we want Xi and Zi, but we want Y1 and L out. Plus, because we want to end up substituting Xi in. So, Xi plus, so F minus V Xi. So we have that. Now what? Well, we know that if we factor this out, F times Z1 is equal to V times Ki plus plus F minus V, or this will be X1 actually. These are all I's. Just for components, because we're going to be substituting in here. If we divide this across, we have Xi is equal to F times Zi divided by V times Ki plus F minus V. Now, if we want to get rid of F, we can simply divide it out, and I'm going to write it a little bit down. We're going to divide top and bottom. So Xi is equal to, because we want Xi alone, but we also want it to really work with Ki minus 1, we have Zi divided by, V over F Ki minus 1 plus 1. V over F is our vapor fraction, which is, say, mole fraction, but it's a percentage of the total that is in vapor, which means that Y or L over F would be the liquid fraction and would be, the amount of, the percentage of the total moles that would be in the liquid phase. So, we can substitute this in here. I'll just draw it down here, make sure you can see that. Yeah, you can see that. That means that if we substitute in Zi times Ki minus 1 divided by the vapor fraction Ki minus 1 plus 1 is equal to 0. Now, we can use this to find to figure out the components of vapor, liquid. So we can find VF, and by that we can find the amount of liquid. We can also find Y1 and X1. We can find the amount of liquid flowing out, vapor flowing out, the constituents in it, etc., etc. And with that, we're going to be going to some coding. Thank you very much for watching.